Okay, Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. We arrive in week 13 of gravimetry analysis, and it's the start one of the classical methods for determination of your analyte. This time is gravimetry, where it's all about weight, precipitate, making precipitate your solution, your analyte in the form of solution, and you convert that into precipitate, and then you weigh how much precipitate are being formed. Now, gravimetry analysis is a quantitative determination of the analyte. So you have your analyte again in the solution itself, and then you will add what we call as a precipitant. Okay, precipitant. Examples. Now your analyte is chloride, so it's soluble in water. So you add silver, and silver is a precipitant. So when silver and chloride react, it will form the precipitate silver chloride. And in gravimetry, you form the precipitate, you wash the precipitate of any impurities, you dry it, and then you will weigh the product and relate how much weight being formed to the original concentration of your analyte in the solution. So this is gravimetric, and the application as stated in the notes. So the criteria is simple. The analyte must be soluble, initially in a soluble form, and when added the precipitant, it will form a very good precipitate, a big precipitate, enough to be filtered, and it can be weighed. Okay, it can be weighed, it can be dried, and it must form a very clear precipitate. Okay, meaning that not clear precipitate, it must form a precipitate of known composition, like silver chloride. So you know what the composition are, and the product hopefully will be pure, and it represents the amount of analyte. Okay, so in the note it says that difficult to obtain a product that is pure, so that's why we do the washing. Okay, and sometimes beside washing, there is some procedure in it called reprecipitation or digestion to improve the amount of precipitate being formed or to purify the precipitate. However, the method is a classical method. As such, it is time labor, okay, time consuming and labor intensive. In your lab, it takes about 2.5 hours for the formation of the precipitate, and then you have to dry it, and then you have to weigh it. So total about one analysis, it will take you around 2.5 hours to 3 hours. Okay, so that's why it's not popular, and since it's a classical method, most of it are in the form of ppm level. You cannot go to part per billion level. Now, what is a precipitate? A precipitate will form when two soluble ions react together and forming a precipitate, an insoluble precipitate of a known composition. So the example that I gave just now, chloride is the analyte, and we add silver to form a silver chloride precipitate. And if you look in the equation, just to be clear, that it is a reversible reaction. Okay, so it can form the precipitate, and that precipitate can resolubilize to form the ions. Silver chloride is a very good example. Now look at the difference between silver chloride and ferric or ferrous oxide. In the reaction, you observe that Fe3+ will react the formation of ferric hydroxide. Ferric hydroxide is gelatinous. It still contains water, so it cannot give you a clear precipitate. So it must further ignite to form ferric oxide. Then only it can easily be weighed into a clear powder, a clear composition, Fe2O3. FeOH, there's still water. There are still water inside. Okay, so that's why we cannot use FeOH3 as our final precipitate. It's an intermediate. So it must be further ignited at high temperature to remove all the excess water to form a good precipitate in the form of ferric oxide. So silver react with chloride to form AgCl without any further reaction. Whereas for Fe, reacting with ammonia and water, the formation of ferric hydroxide, you must further ignite it to form Fe2O3. Then only we use the final weight Fe2O3 as our means of calculating back the concentration of the original solution. There are methods of thermogravimetry. So that is a reaction just now, the first one. This is based on the volatilization method. We would not discuss this in this topic. Okay, the solubility of the precipitate. So if you look at the example again for AgCl, so you are writing it, look at how it's being written. So AgCl dissociate into its ions. Why? If you look back of how we write the value of K, for any reversible reaction, there will be a K. And K equal to the concentration of the product over the concentration of reactant. Okay? So by writing this way, so this one, the KSP, it can be Ag plus Cl minus divided by 1. So that's why it's preferred to write this way, because always K is product over reactant. What SP? SP is solubility product. What is a K? K is the dissociation constant based on solubility product of a slightly soluble salt AgCl. Okay, and the equation for KSP and the reactions is based on the written part. Okay, so any coefficient is powered to the concentration. Okay, so you see the value of A over here. A is the coefficient and it will be powered, and B is to be on the power part. So KSP is any of the coefficient powered A and to the power B. Look at the example. How do we use the term KSP? For AgCl, AgBr, AgI, look at the value. So as the value of KSP increases, okay, as the value of KSP decreases, because if you can observe, it is in the form of minus, meaning that the ability for it to form precipitate will increase. Okay, as the value of KSP is smaller, the ability to form precipitate increases. So if we look at the value between AgCl, AgBr and AgI, so AgI has the smallest value, meaning that in a solution containing Cl minus, Br minus, I minus, so if you have a solution of all the three, chloride, bromide and iodide in a container, and you add silver, what happens? Since AgI has the smallest value, so all the silver that is being added will react with iodine, the formation of AgI, until all the iodine are exhausted, and then only excess silver will react with bromide. And all bromide exhausted, and then only all the added silver will react with chloride. Okay, so meaning that when you add silver, it does not react with all the ions. No, it will react preferentially with the compound that has the lowest KSP. In this case, is AgI, silver iodide. So this is how we make comparison. Which precipitate will form first? The smallest KSP. So these are further example of KSP solubility products, expression for other compound that can form precipitate. How do you know it form precipitate? Look at it, the S. Okay, so all this S shows that all the ability to form precipitate. Okay, and then I'll just remind you back this sign. Okay, this sign, it means that the solution is in the concentration used is in molarity. So all concentration are in molarity. If you are not in the form of molarity, you have to convert it so that it will be in the form of molarity. So can you understand how it's written? Let's check back. Okay, so again this one 1 and then this one 2. Okay, refer to the coefficient. So similarly, this is the coefficient, and this one is 1, and then this one is coefficient 3, and then this coefficient 2. Okay, so that is how the KSP is written. Okay, based on the ions, and the coefficient is being put up as the power. Now let's make some calculation. Okay, example of the calculation. Okay, calculate the solubility of AgCl in a saturated solution of AgCl. So KSP basically relate to when the solution becomes saturated. What is meant by a saturated solution? When you add further the amount of solute, okay, if you add solute into a solvent, it becomes solution. So as long as it does not become saturated, further addition of your solute, it will continue to solubilize inside the solvent up to a point where it becomes saturated. That point is based on the value of KSP. Okay, so KSP for AgCl is 1.10. So meaning that when we mean the concentration of Ag plus times the concentration of Cl minus, it must be equal to the KSP. Now let's put example. If I were to have a concentration of Ag plus or Cl minus, sorry, Cl minus, I'll draw it, and the Cl minus is 10 minus 4. So how much of the Ag plus that I should add so that it becomes a saturated solution? So KSP is 10 minus 10. So the original concentration of Cl minus is 10 minus 4. So how much silver that you have to add? So that is equal the value of KSP, which is 10 minus 10. So you have to add 10 minus 6, right? So that is equal to the value of KSP 10 minus 10. Now, if I were to change now this Cl minus rather than -4, I change now that it becomes -7, which is a very low concentration. Okay, so the concentration of Cl minus is 10 minus 7. So what is the amount of Ks silver that we have to add? So it becomes 10 minus 3. So depending on the original concentration, if we decrease the concentration of chloride, we have to increase the concentration of silver, so that when both are being multiplied together, it will produce 1.0 times 10 minus 10. Okay, so that's how what we meant by the calculation of the value of KSP. And how much silver will react with Cl minus? It will react with the amount of Cl minus, so that it will have a value KSP of 1.0 10 minus 10. If the concentration of Cl minus is high, only a small amount of Ag plus have to be added. If the concentration of chloride is low, then a high concentration of Ag plus need to be added. Okay, this one is when it is of equal concentration. Okay, let me put it again. What is S? So S is the term given as molar solubility. Okay, so what is the molar solubility? Is 1.0 times 10 minus 5. So the molar solubility of AgCl is based on the value of S. Okay, this is quite tricky, so you have to listen to me very carefully. So if you look over here, okay, compare the solubility of AgIO3 and LaIO3, in which given AgIO3 is 3.8 3 times 10 minus 8, whereas KSP of LaIO3, lanthanum iodate, is 6.5 times 10 minus 12. So when we are comparing this now, based on AgI, AgBr, and AgCl, we see that the smaller value of KSP, it will form precipitate, the easiest. So AgI has the lowest KSP. As such, it will have a lower solubility. Okay, a lower solubility. Lower solubility meaning that easier to form precipitate. So when we are make the comparison here, so what do you expect? Since LaIO3 has a lower KSP, so it will precipitate. It has easier to become precipitate. Okay, I will say to you no. Why? Because in AgI, AgBr, and Ags, the value is 1 to 1. Ag is 1 to 1 ratio with Br, okay, or with the iodate, is a 1 to 1 ratio. Whereas for lanthanum, is a 1 to 3 ratio. 1 to 3 ratio. So meaning that when it has the same ratio, you can compare. AgBr, AgCl, AgI, you can compare only based on the KSP. But when it has a different ratio, in this case, this is 1 to 1, this case is 1 to 3, you cannot compare just based on the value of KSP. You have to make the calculation. So in this case, it makes the calculation for the for S. So for S value for argentum iodate is 1.3 times 10 minus 4. And for lanthanum iodate, so look at the this is S, and then this 3S cube. Can you observe it? It's a 3S, and then you cube it. So it becomes 27S4. And calculate the S, you get it 7.0 times 10 minus 4. Okay, I remind you back, please make sure you understand this, observe this. Okay, so S is for the lanthanum, and then the 3S, okay, 3S over here, you bracket it and then you cube it. So it becomes 27S4. And the solubility of the iodate, okay, the S is 7.0 times 10 minus 4. So now you compare the value. What do you observe? Lanthanum iodate has a higher value of the S, meaning that it is more soluble or less to form precipitate. And argentum iodate, it is less the value of S and is easier to become precipitate. Okay, so although KSP of argentum is bigger as compared to KSP, but when we made the calculation for the value of S, we found that lanthanum iodate will become precipitate much easier as compared to argentum iodate. So that's how we make the calculation, which have the lower solubility. Okay, why don't you try to make this calculation? Calculate the value of KSP, calculate the S of this, and this one calculate the solubility product, KSP of PbSO4. Now, again, I've told you just now that all the value of concentration must be converted to molarity. Must be converted to molarity, and then you can calculate the value of KSP. So over here, it's not in the form of molarity, it's gram per liter. So you must convert it to be in mole per liter, then only can you calculate the value of KSP. Okay, change it, and then it's easy to make the calculation. Okay, try this at home. Okay, why don't you try to make this calculation? Calculate the value of KSP, calculate the S of this, and this one calculate the solubility product, KSP of PbSO4. Now, again, I've told you just now that all the value of concentration must be converted to molarity. Must be converted to molarity, and then you can calculate the value of KSP. So over here, it's not in the form of molarity, it's gram per liter. So you must convert it to be in mole per liter, then only can you calculate the value of KSP. Okay, change it, and then it's easy to make the calculation. Okay, try this at home. Okay, what are the 4 factors that influence the properties of precipitate? Okay, the formation of the precipitate, what factors that influence precipitation so that it can occur very well? Okay, the first one is based on temperature. What do you expect? Higher temperature, more soluble, many things become. Okay, the lower the temperature, the lower is the solubility of the precipitate. So meaning that it's easier to form precipitate at a lower temperature. It is easier to be soluble at a high temperature. Okay, for example, AgCl at 100 degrees centigrade, it is more soluble, as 25 times more soluble as compared to at 10 degrees centigrade. Barium sulfate doubles, okay, its solubility, meaning that it will dissolve when the temperature is raised from 10 degrees centigrade to 100 degrees centigrade. So as temperature increases, precipitate decreases. The second one, effect on pH. Okay, let me tell you. How do you know in an equation in which the reaction is being affected by pH? Quite easy. Look at over here. Either you have H plus, meaning that the reaction is now in acidic form, or OH minus. Okay, so these are indicators that the equation is being affected by pH. Okay, now let's discuss it. What happens when you increase pH? When you increase pH, the concentration of OH minus increases at pH. So Le Chatelier says that, okay, Le Chatelier principle, it obeys the rule of Le Chatelier. When you add the concentration over here, okay, when it says that when you changes any form, pressure, concentration, temperature, to a reaction that is already stable, so it will force the reaction to occur to change, so as to offset the changes that you make. Alright, you add now, you increase the pH, meaning that you increase the OH minus. So what happens? You increase the concentration and the reaction will move to the left, or more precipitate will be formed. Okay, so in this case, more precipitate will be formed at high temperature. When you add at high pH, as if you are adding more OH minus. What happens when you add H plus? So when you add H plus, it will react with the OH minus. So the concentration of OH minus decreases. So what happens? More magnesium hydroxide will dissolve to replace the OH minus that had been lost. So what happened to the precipitate? Less precipitate will be formed. Okay, so the precipitate will decrease. So in the answer, it says that the solubility of magnesium hydroxide increases, okay, or the precipitate decreases. So that is effect of pH. So if we make the calculation, okay, aluminum hydroxide, so this is the equation. Now again, look at what I like you to observe. When we are putting based on S just now, okay, if we are calculating using S, this one is 3S. But when we are now putting in terms of the OH minus already in the form of concentration, so we do not put the 3 OH minus over here. Okay, can you understand me? I do not put the 3 OH minus over here. Instead, it's only OH minus. But when we want to do it in the form of S, we put the 3S over here. Okay, so this OH minus, and then we power the coefficient 3. But there is no 3 over here. Okay, there is no 3, meaning that there is no 3. So 0.1 times OH minus Q. And then you will calculate the concentration of OH minus, that is the concentration. So at pH, so this is the POH, at pH 6.77, it is the same as the value of KSP. Okay, so you must increase at at the value of KSP, the precipitate does not form as yet. It must be higher than the value of KSP, so that it becomes super saturated, then only the precipitate will form. So at pH bigger than 6.77. Okay, again I remind you, please make sure that you understand it. When you are making calculation based on solubility, then you put the 3S over here. But when you make the calculation based on the ions, you do not have to add 3 at OH minus. Okay, effect of solubility of precipitate. Okay, the term unsaturated, saturated, and supersaturated. Let me give you the same example just now. So when you have chloride as your analyte and you add silver plus as your precipitant, so initially you will, when you add Ag plus, some precipitate will form, but it will redissolve. Okay, it will form AgCl, but it will redissolve first because it's still in the unsaturated. So finally, everything in the form of dissolve. Up to a point, when you further add the amount of Ag plus, up to a point of saturation. So saturation is where no more Ag plus. When you add Ag plus, all Ag plus will react with Cl minus. But the precipitate does not form as yet. So when you add a further amount of Ag plus, so the solution now becomes supersaturated. Okay, supersaturated. So when it becomes supersaturated, then only at this time precipitation will occur when the solution had become supersaturated. Now, how much of the solution it become precipitate? Only a small amount will become precipitate. Okay, so this precipitate and the above is a saturated solution. So this precipitate form and the above solution above the precipitate is in saturated form. But if you were to add a lot of Ag plus extra beyond this saturation point, then a lot of it will become precipitate. But still the solution above the precipitate is in the form of saturated solution. We can predict whether a precipitate can form or not by comparing the value of Q. Okay, so Q has the same formula as KSP. So meaning that if either Q or KSP has the same formula, Ag plus Cl minus. Okay, it's the same formula. But the difference is, next slide, Q, when you are a KSP, sorry, I put it as KSP first. KSP is the concentration of Ag plus and the concentration of chloride at equilibrium. Whereas for Q, it's the concentration of Ag plus and Cl minus other than at equilibrium. As most often you can look it at when you start your experiment. So Q is when you just want to start your experiment in which you add Ag plus to chloride. And KSP, the value KSP is the value of chloride and Ag plus at equilibrium. So now you compare the value of Q with the value of KSP. So if Q is less than KSP, meaning that the concentration you start off is small, so you will certainly say that the solution, the resulting solution, will not be supersaturated. When it's not supersaturated, certainly it won't form any precipitate. It's still in the form of unsaturated. So when Q equal to KSP, so it still reaches the concentration of saturation. Is there any precipitate will form? No. Until the value of Q is bigger than KSP. Then only the excess value, okay, excess value, that amount will form the precipitate, and the solution of above the precipitate is equal to the value of KSP. So you can only form precipitate when the solution Q, okay, the concentration you add, it will form a supersaturated solution. Okay, there is an effect what we call as common ion effect. Okay, common ion effect is that, for example, being given as barium sulfate being dissociated into barium 2 plus sulfate. So if in the condition of the experiment we are doing it, there is an excess sulfate other than the source from barium sulfate, or there is an extra source of barium 2 plus other than the source from barium sulfate. So what happens based on Le Chatelier principle, if you add the concentration of sulfate or if you add the concentration of barium, the reaction will favor going to the left, or formation of more barium sulfate. Okay, I repeat myself. So when we add sulfate, when the experiment is being carried out in an environment in which there are excess sulfate from other source other than that is dissociated from barium sulfate, so sulfate from other source. So when we add that sulfate into that reaction, so what happens? The concentration of sulfate will increase, and based on Le Chatelier principle of when system is already at equilibrium, so the reaction will favor moving toward the left, or the formation of more barium sulfate precipitate. So this effect is what we call as common ion effect. Okay, this is the example being given for calculation as to illustrate common ion effect. Comparison for the solubility of PbI2 in water at the environment and 0.20 in 0.20 molar sodium iodide solution, in which there is an increase of iodide not only from the PbI2 but being supplied by sodium iodide. Okay, from the first one, so we make the calculation, the normal calculation. So S to S, then for S cube equal to 7.9 10 10 minus 9, and the solubility S, the molar solubility S is 1.3 10 10 minus 3 molar. Now we make the calculation then for the when lead iodide in 0.20 molar sodium iodide solution. As such, the S for iodide comes from PbI2 and also 0.2 molar coming from sodium iodide. Now they make an assumption the S from the I2 is very small. Why? Because the KSP is very small, 7.9 10 10 minus 9. So the supply or the contribution of S is small relative to that contributed by sodium iodide. So 0.2. So it means that we make now the assumption that all the iodide is contributed by sodium iodide because the amount is less. Okay, the amount is less from PbI2, small comparatively. So even now we only considered iodide only from sodium iodide. It should be more. Okay, so we make the calculation, and now the same calculation as above. Okay, and now we found that S equal to 2.0 times 10 minus 7 molar, which is a smaller number, or in the term that we made for this, at lower S, meaning that it will form more precipitate. Okay, so this example of what we meant by common ion effect. When the supply of one ion, not only from the original precipitate, but from the environment in which the reaction occurs. Number 4 is effect of precipitating agent used to precipitate our analyte. So the choice of a good precipitant. Okay, if you look over the notes, okay, so precipitants are reagents that have the ability to be selective. So what is meant by selective? There are a lot of ions, and yet it's very specific to our analyte without precipitating all the other ions. So that is what meant by a selective precipitant. Okay, and then the choice of precipitant depends on the capability of the reagent, first to be selective and to be easily filtered, because in the following step after formation of the precipitate, we have to separate between the precipitate and the solution, so by filtration. So it must be big enough, okay, large enough to be able to be filtered. So that's why it says that the choice of precipitant, so when it forms precipitate with your analyte, it will form a large precipitate so that it can be easily filtered, and the reaction must be reproducible. Okay, you can do it today, you can do it tomorrow, but the same reaction should occur. Okay, there are two types of precipitant. The first one is inorganic, okay, and the second one is organic precipitant. Okay, the first one is inorganic precipitant. Okay, look at this table. So you will form slightly soluble salt. So if you look over, which is the analyte? So for example, aluminium is the analyte. Let me put it bigger. So aluminium is the analyte. Now, if you look over, the precipitant comes in the form of ammonium hydroxide. So you have your analyte and you add ammonium hydroxide. Now, not the total ammonium hydroxide will be the precipitant. Instead, only OH is the actual precipitant for it to become aluminium hydroxide. Okay, aluminium will react the precipitant aluminum hydroxide, and if you observe the precipitate form, and this is the precipitate way. Okay, I'll go first about the procedure. When the precipitate already formed, so for any hydroxide, most hydroxide, it is gelatinous, as we discussed below before this, meaning that there are still water. So it has to be changed into a form in which it is easily will become precipitate where there is no more excess water. So that's why for hydroxide, aluminum hydroxide, for ferric hydroxide, it had to be further ignited so that the final product is Al2O3, Fe2O3, and this is the type of precipitate that will be weak. Okay, now look at the second example, silver. So when you look at the precipitate form, you know what is the real precipitate. So if it is AgCl, so this is the analyte, then it must be HCl, but you add HCl, of course. So Cl minus is the real precipitate. So if you use Cl as the analyte, so you see the product is AgCl, so Ag is the real precipitant. So what happens to nitrate? Nitrate, we call that a spectator ion. Okay, nitrate is the spectator ion. Ion that is present in the solution, but it is not involved in the formation of the precipitate. It is still remain in the solution, and this is what we call as contribute to what we call as impurities. To have a pure AgCl, we have to remove that nitrate. So in the above example, we have to remove the H plus from HCl. We have to remove the ammonium from ammonium hydroxide. So this serves as impurities to the purity of the final form of our precipitate. So similarly, if we go down table, okay, barium is the analyte and barium sulfate is the precipitate. Okay, so we add sodium sulfate, meaning that what is the precipitant? Sulfate. What is the spectator ion? Sodium. Okay, that's how we look at the inorganic precipitant, which one is the real precipitant and which one is the spectator ions. And now these are organic precipitants. So organic precipitant, if you look over the difference between the name is dimethylglyoxime, and let's see the difference dimethylglyoxime and carbofuran and hydroxyquinoline. And on the right are all the ions that can be precipitated by using this organic precipitant. Okay, look at the difference. Is there any difference? Yes. What's the difference? DMG or dimethylglyoxime, it can only precipitate with 3 ions: nickel, palladium and platinum. I'm not sure. I think cobalt also can be precipitated by DMG. Okay, but it listed only 3. Whereas carbofuran, there is 2, 4, 6, 7. And hydroxyquinoline, there's a lot more. So what we will say, dimethylglyoxime is a very selective precipitant, in which if there are the number of analyte in such as in hydroxyquinoline, it will only bind with nickel, palladium and platinum only. Would it react with copper? No. With zinc? No. With magnesium? No. 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 It will only react with dimethylglyoxime, even in the presence of a lot of other ions. So this is what we call as a very selective precipitant. Whereas oxine or hydroxyquinoline is what we term as a general precipitant, where it can precipitate out with a lot of ions. So these are the difference between the type of organic precipitants. Okay, when organic precipitants are added to the metals, it will form a chelate compound. So when it forms that chelate compound, it will attach not only to one part. Okay, the metal is not attached only to one part of the compound, the organic compound, but it will attach to 2 parts or more. So what we call as chelate. Okay, chelate compounds, so that the metals will form a very strongly bound precipitate. Depending on the molecular weight of the precipitant, most organic precipitant will have a large molecular weight comparatively to inorganic precipitant. So if you were to be precipitate with an organic compound, so depending on the size of the organic compound, so if it has a large molecular weight, so it will have a large molecular weight precipitate, and it will produce a large weight of the precipitate and will easily be filtered. Okay. As mentioned just now, DMG is very selective. So when we being selective, so it's a good choice of precipitate. But some may not be selective. Okay, hydroxyquinoline may not be selective, but by controlling pH, we can make it slightly more selective by controlling the pH. And under normal circumstances, precipitates with organic reagents are often coarse and bulky, and hence easily being precipitated out, and you will see a lot of precipitate will be formed. Okay, so this is the advantage of organic precipitant as compared to when we are using inorganic precipitants. Okay, example. Hydroxyquinoline, is it selective? No. It can precipitate out a lot of compound. But it can be made to be slightly selective when we control the pH. So it gives you an example. Aluminum ion can be precipitated out at pH 4. Okay, so by controlling the pH, when at pH 4 we put into a solution containing aluminum and magnesium, so it will only precipitate out aluminum. Once the precipitate is over, so we increase the pH, then it will react with magnesium and form the precipitate with magnesium. Okay, so that's what we mean by controlling the pH. We can make the hydroxyquinoline, a general precipitant, to be more selective. Okay, let me take the opportunity over here. So you see Mg, it will bind with this molecule. Okay, over here. Okay, one molecule of over here. Now, to this same molecule, it can bind at 2 places, 1 and 2. So this is what we meant by the chelate just now. Binding with the same molecule, but bind it at more than 1 places. So it will form a more stable precipitate. So this is what meant by the chelate just now. Now look at formation of nickel DMG. Okay, nickel DMG. Look at the size of the nickel DMG molecules. Okay, so this is nickel and this is a DMG. So if you look over, so this is the form of nickel DMG compound or chelate. So it's so bulky. So we expect the red color when you do the experiment in the lab. So nickel, when we add with DMG, so it will form nickel DMG red color precipitate. Okay, so this precipitate is bulky in the sense that it can be easily filtered. Although for some group, I observed that some of the precipitate, when we make the filtration, some filtrate will form red color, meaning that the precipitate form, there is a problem. It formed very small, what we call as colloidal. So it passed through the glass frit and being filtrated out. So it's not being filtered. So this is the problem which we'll go in the next chapter of how to produce large precipitate through particle growth and not through colloidal. Okay, but we make the assumption now, when we use the DMG under normal circumstances, if you do it very well, it will form a bulky precipitate of nickel DMG. Okay, Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. Now we go to the second part, the steps in gravimetric analysis, or exactly how in the experiment that we do the gravimetric analysis. Okay, the real steps in doing the experiment. So it's listed over there. So sample preparation, drying, weighing, and dissolving, and then we add the precipitant. So it will form the precipitate, and that precipitate, if needed, we do digestion. If not needed, then step 3 is not needed. Then if for filtration, we filter it to produce the precipitate. Okay, to separate the filtrate from the precipitate. So and then we will wash to remove all impurities. We'll dry it, and ignition when it form hydroxide. Okay, normally we will only dry it, and weighing to a constant weight when we know that all water had already been evaporated, and then there will be a calculation. So these are the steps, and we'll go it one by one. So in terms of sample preparation, there's not much to be discussed over here. So it is solid, and then it will dissolve in a suitable solvent. But in your lab, for example, you are being given in the form of liquid. Okay, in the form of a liquid. So there's not much for me to discuss over here. So you prepare a solution. As in the lab, you are given a solution of nickel, for example. So there is preparation of your sample. Okay, to the precipitation and forming of precipitate. So when we add your precipitant to your analyte, and it will form a precipitate. So what kind of precipitate that we want? So mentioned before that we want to have a large precipitate. So that it will be easily to be washed and easily to be filtered. So that is a perfect precipitate that we want. It must be large, and then it should be free from impurities beside the spectator ion. Okay, so certainly you cannot remove the spectator ion when it forms the precipitate. So you will remove it by what we call term washing after it has formed the precipitate. But other than that, other sources of impurities, it should be tried to be prevented. Okay, any foreign ion that may enter or may affect the purity of your precipitate. And finally, that precipitate should be insoluble enough. Okay, minimal dissociation. How to have minimal dissociation? A good precipitate which have the KSP value which is very, very low. Okay, more negative, big negative, minus 19, minus 17. That is an ideal precipitate. It is almost insoluble, but it is soluble because it can go reversible reaction. But we say that it is the term almost insoluble. So that is an ideal precipitate. So hopefully we can form a precipitate which is large, pure, and have a low solubility. Okay, let's look now at the step in the precipitate formation. You have your analyte, Cl minus. So again, I've mentioned to you, if you cannot have Cl minus in free form. You have it normally you add sodium chloride, for example. Okay, sodium chloride, and that sodium chloride will provide you the chloride. So that is your ion, your analyte. So is there any other extra ion? Yes, sodium. So sodium serves as the spectator ion. And then you add your precipitant, Ag. Okay, Ag plus. But it came again as a molecule, or as a ionic, is an ionic salt. Okay, so it comes as Ag nitrate. So Ag plus will react with the chloride, but beside that there are still two ions which is in excess, does not involve in the reactant, spectator ion. So from the analyte we have the sodium plus, from the precipitant we have the nitrate. So these are the the spectator ion that need to be removed to get a pure AgCl crystal. So the first thing, we must add in a concentration in which the Q, the value of Q, must be bigger than the value of KSP, so as to achieve the supersaturation status. Then only all the precipitate can form. Okay, so that is based on calculation. So when you make your experiment, make sure that the value of Q is bigger than the value of KSP of the particular precipitate that you wish to study. Okay, when you add the precipitant, it will undergo what we say as nucleation. Okay, termed as nucleation, a process where molecules in solution join randomly to form a small nucleus of AgCl precipitate. So we call it nucleus. It's a very, very small nucleus. Okay, so then there will be, let's put just a number so that we can easily understand. Okay, for example, it will during the nucleation stage, it will form 20 nucleus. So meaning that 20 small particle of AgCl. And then by controlling your experimental parameters, okay, by controlling it, it can proceed into two ways, either by particle growth or by nucleation. Okay, so again I repeat myself, it started off from nucleation, okay, from nucleus, and then when you control your experiment, we can change it from nucleation to be particle growth. Or if you don't control it, it will continue with the process of nucleation. Okay. Now, so what does this mean by when it continues by process of nucleation? Just now when we say when it started by nucleation, so we knew that when it goes continue by nucleation, when more nucleus are formed. So originally it's 20, then it's become 50, then it's become 80. So that is what we say as it continue with the process of nucleation. And the resulting precipitate will be in the form of colloid. 1 to 100 nanometers. Very, very small. Just a little bit outside. SARS-CoV-19, the virus, what's the size? Okay, it's a big virus, and the biggest is 121 nanometers. 121 nanometers is the size of the SARS-CoV-2, which caused the COVID-19 problem right now. So it's from the virus SARS-CoV-2. So the size, the biggest of the size is 121 nanometers. So it's a large size. Most of the virus, the virus is a large size. Okay, so the size of colloid. So the problem when it forms colloid, okay, so when you filter it, the one that I've told you just now, when some of the filtrate is red in color, you look into the conical flask, it's red. The filtrate passed through the filter, it's red in color. That means that the process that undergoes just now is the process of continuation of the nucleation. So it started from nucleation and it continues to be in the nucleation process, and it will produce a small particles, small precipitate, which we term as colloidal, very, very small. But if we control it very well, controlling the concentration, controlling the solubility, controlling the mixing it, okay, stirring it very well, then the nucleation process will change to what we call as particle or crystal growth. What does that mean? Okay, rather than it form a new nucleus, instead right now a new molecule, a new precipitate will grow onto the existing 20 nucleus just now. So it will form on the original nucleus and it will grow on that. So what happened to the number of nucleus? It won't increase. So it still remain as 20, and new precipitate formation occurs on the existing nucleus. So that nucleus is few, but it will become large due to what we call as particle growth process. And that particle growth process is based on how we control the formation of the precipitation process. Okay, finally it will produce coarse crystal, large precipitate, and this is the ideal precipitate that we want to form. It goes by particle growth. So this is basically the explanation, the induction period, the time of the first, when we add the precipitant to the analyte. So it takes certain time, and then started off with the process of nucleation, formation of small nucleus of your precipitate, and then hopefully by controlling the parameters, we can hopefully that it will proceed then by particle growth. So the particle growth, the addition of ion of the precipitate on the existing nucleus. Okay, so if you look as the term over here, let me put it. Okay, excess ion. So excess ion is the spectator ion just now. So the spectator ion hopefully is it will collect around the precipitate. So it will be in the solution. It will be in the solution. You have to remove it by the process of washing later on. Okay, I put in the words just now, by controlling the parameters, by controlling of how we do the experiment, hopefully it will proceed by particle growth, producing large precipitate. What does it mean? Okay, so we call it relative supersaturation on the von Wieman ratio, Q minus S divided by S. So what is meant by the relative supersaturation? Okay, to form the precipitate, it must be, the solution must be supersaturated. But we must control the term Q. Q is molar concentration of the mixed reagent, so that the Q will be small, and making the solubility to be large. So if I were to put relative supersaturation, RS, okay, relative supersaturation, how to make it small? So the numerator will hopefully can be small, and the denominator to be big. Then we have the relative supersaturation to be small. If it is RS, or relative supersaturation is small, then it will produce large precipitate. So that's what it means. Okay. So in the von Wieman ratio, it says that to have a big precipitate, then you must have a small relative supersaturation. To have a small relative supersaturation, the denominator should be big and the numerator should be small. So how to make it that way? Q, or the concentration, must be as low as possible, and S, the solubility, must be as large as possible. Okay, let's discuss it in the next 2 or 3 slides. So large Q minus S, then it will proceed by nucleation. A small Q S, then it will proceed by formation of particle growth, and large crystal will proceed. Now, what is meant by large supersaturation or slow supersaturation? I don't know how to discuss it, but let me try. If I were to have what this is as the saturation. Okay, so this is supersaturation, this is unsaturated, so this is the value of KSP. So what it means by small supersaturation, when you increase in terms of supersaturated, when you add your solute, okay, the precipitant, when you add your precipitant, make sure that the precipitant and the analyte concentration do not go too much into supersaturated. So instead, you have it just at small, okay, at a time, so that it just becomes small increase of relative supersaturation. It becomes slightly supersaturated so that it can form the precipitate, rather than a large increase of supersaturation. So I think that is what is meant by large and small. Make it small so that it can go by particle growth. Now, how do we control it? So that it will have a Q is small and S is big. Okay, so the first one is by precipitation from dilute solution. So when you make your solution, make sure that you do not make it in high concentration. Okay, so it is made in dilute solution, and then you will add it slowly. So that is how we control the Q, so that it will be small. Secondly, further in the following slide, they will further discuss precipitate with stirring. Now, when you add, we normally add it by puree. Okay, when we allow the solution precipitant to go into the solution, so what happens? What we call as a lot of local increase, a small part of the solution, when it receives the part that receives the precipitant, it will have a high concentration. So without stirring, that area will have a high concentration, and it will cause what we can say as the Q will increase very high. So we don't allow it. So that's why when we add our precipitant, it must be adding with stirring, so as we will distribute all our solution to all parts of the solution and prevent that what we call as local excess of the reagent. So that's the function of stirring. If you can remember while doing your experiment last time, okay, I saw you doing the stirring. But why do you stir? I don't think so, you know it, right? But you stir because in the procedure said do it with stirring. So that the purpose of the stirring, so that all new precipitant being added is being redistributed into the whole of the solution, so that it remains in small concentration, low concentration. Okay, so stirring will promote low concentration. Now you heat it at around 80 plus temperature, I suppose. So when at high temperature, the solubility will increase, the solubility of the precipitant. Okay, and the reaction occur at high temperature. So the solubility of the precipitate increases with the temperature, and you will precipitate it at low pH. So at low pH, the solubility will increase. Okay, normally, okay, at low pH, solubility will increase. And then the last two, there's a separate discussion for it, what we call as digesting the precipitate, digestion. But this digestion in gravimetry is not the same as digestion in your sample preparation last time. It's totally two different things, but the name still remains the same. digestion of the precipitate. Okay, and the last one, precipitating from homogeneous solution, will be described a little bit later. And these are the description just now. Precipitation from hot solution, so molar solubility will increase. Okay, so an increase in air decreases the supersaturation and increases the size of the particle. Precipitation from dilute solution, so the Q will be low. Okay, and this is just facilitated by our stirring, so that keeping the Q concentration to be low. And then precipitation at pH near the acidic end of the pH range, so at lower pH it will be the solubility will be low at lower pH. Okay, and digestion of the precipitate, I won't discuss this now. Okay, I will do it later. And precipitation from homogeneous solution. Okay, you have to listen to me quite carefully. So this is a technique where a precipitating agent is not added but slowly generated throughout the solution by a slow homogeneous chemical reaction. Let's put it this way. Okay, when you are adding the precipitant, you are not adding it in one shot. You just add everything in one shot. It will keep the Q very, very high. Okay, instead it's appropriate or suggested that if I were to do it, I will put it into a burette, and I will allow only a small concentration to pass through, and then with the aid of stirring. So I put the precipitant in the burette, and then I have a stirring mechanism, stir bar, and then I continuously stir the solution and add the precipitant drop-wise. So this drop-wise allow Q to be kept low. Okay, Q to be kept low, drop-wise, but it takes a lot of your time. Okay, a lot of your time. But the resultant precipitate, it will be coarse and big, so that it will form through the particle growth. So how it's being, what is meant now by precipitation from homogeneous solution is based on the next slide. Okay, urea. Okay, urea, it generates OH minus ion. So the precipitant here is the OH minus ions. Okay, so what do you do in these examples are being given? Okay, so you add urea in one shot to your analyte. Okay, you add urea into the solution containing your analyte, and then you leave it for a certain period. So what happens, this urea will dissolve or dissociate slowly, and in the process of dissociation it will release the OH minus ion slowly, and this OH minus ion will then react with your analyte. I'm not sure what you are studying, so depending on the analyte. Now, so in homogeneous precipitation, we are adding our precipitant slowly. Okay, slowly, but we do not physically do it. We add urea in one shot, but urea dissociates slowly, releasing OH minus. So it's as if we put it drop-wise. So OH minus is slowly to be released by urea and react with your analyte. So this is what we meant by homogeneous precipitation. Okay, urea is added in one shot. You put in urea into the solution, but that urea will release the OH minus slowly, and this will promote particle growth and large precipitate. Okay. Okay, let's look example of how a precipitate is being formed. The example of what we meant by the precipitate. Now, the example is the same example based on the formation of AgCl precipitate, and we will use the precipitant Ag nitrate. Okay, silver nitrate added to Cl minus ion. So as stated over here, Cl minus ion. So again, as I've mentioned just now, you don't add Cl minus. It must have a counter ion, so it in the form of originally from HCl. Okay, sorry my writing. Okay, HCl. So there will be an excess H plus. Okay, so H plus is the spectator ion. So Ag nitrate. So Ag is the precipitant. Nitrate is the spectator ion. So what happens? Let me draw it. So it will form the crystal Ag nitrate. Ag chloride. So this is the crystal. Ag plus Cl minus, Ag plus Cl minus, and this is hopefully the crystal that we want to form. Okay. Now what happens when you add your Ag nitrate to the formation of the chloride? You will always make sure that all chloride will be precipitated out. So you will add more than enough Ag plus. So there will be an excess of Ag plus. Okay, it's logical. So you will add. You know that the concentration of Ag plus needed to form precipitate with all the chloride expected. So you put in excess Ag nitrate. So if we were to see, so if this is all the precipitate, so actually it will have a two layers, what we call as a double layer. So let me try to illustrate it if I can. So the first layer is the layer that is very close to the precipitate. Okay, and I expect this to be the second layer. Okay, can I redraw it? Just a moment. Okay, let me draw it again. So I expect this to be the first layer. It looks better. Okay, now, so this is what we call as the primary layer. Okay, and this is the secondary layer. In theory, it says that the primary layer consists of atoms that in excess that is similar to what is in the crystal. I'll put in another way. So the first layer consists of excess atoms that is similar to the atom in the precipitate. So what is the precipitate consist of? Ag plus Cl minus, right? Now, is there any excess Cl minus? No. Every Cl minus should be precipitated out. Is there any Ag plus, excess Ag plus? Yes, there will be excess Ag plus. So Ag plus is the adsorbed ions on the primary layer. So if you look over here, there's Ag plus, Ag plus, Ag plus, Ag plus, Ag plus as such. Okay, so all of this showing that the primary layer consists primarily of Ag plus, and the secondary layer will consist of all the excess ion or spectator ions. What is our spectator ion? From the Ag nitrate, so there will be nitrate ion. Okay, so there will be the nitrate ion, and then from the Cl minus there will be the H plus. So all these are ions that come from HCl. Okay, so Let's put it as a summary, for example. So when the precipitate forms, so it consists of a crystal, Ag plus Cl minus, Ag plus Cl minus, but there will be a formation of two layers, double layer, what is termed as a double layer. So the first layer consists of ions that is similar to the crystal that will absorb in the first layer. So Ag plus is the excess ion. And the secondary layer will consist of the spectator ion, the nitrate and the H plus. So this is what happens, example of precipitation mechanism. So this is further discussed. So this is the slide. Just explain again what I tell you just now. Okay, the counter ion, or I call it as the spectator ion. So it will be in the second layer, and the first layer will consist of the Ag plus. That is the excess Ag plus when we are doing the addition of precipitant. Further term, adsorption. So adsorption is a surface phenomena. Okay, a colloid is very small, and the electrical double layer, again just now as mentioned, the negative and positive layer, the primary layer and the secondary layer. Okay, this is another example, illustration of the formation of barium sulfate as BaCl2 is added into sodium sulfate solution. Now, which is the analyte? Which is the analyte? So let's look. You have a barium sulfate precipitate, right? So which is the analyte? So it says that barium chloride is added into sodium sulfate. So we know that sulfate is the analyte. Okay, sulfate is the analyte and barium is the precipitant. What then is the excess or spectator ion? Spectator ion is sodium and chloride. So what do we expect? So barium sulfate will be the the crystal of barium sulfate, and then in the first layer is an excess of your precipitant. So what is your precipitant just now? Barium. So that's why it says barium, barium, barium in the first layer. And in the second layer, you have excess of chloride, and you have expected, yes, excess of sodium. Okay, it doesn't show sodium here, but you can put, I put it now. So sodium will be in the second layer. Okay, so this is how the arrangement is. So from the crystal, primary layer consists of the excess precipitant, and the secondary layer consists of the spectator ion. Now only we come to the terminology digestion. So I remind you again, this digestion is totally different than what is meant by the digestion while we are doing sample preparation for inorganic when determination of metals. Okay, so in that digestion we add acid to remove organic matrix, but this digestion is totally different. So listen to me please. If we have a problem, so the problem is we are now producing not a big precipitate, instead we are producing colloidal precipitate, and probably result from the process of nucleation instead of particle growth. So what can we do? If you were to filter it, then certainly you will see that red color, the one that I mentioned to you, the filtrate will be red if nickel DMG. that shows that the particle or the precipitate form is very small. It passed through the filter paper. So how to produce? How after you already make the addition, how to produce back that large precipitate? So what we do after you observe that it form very small precipitate, do not filter it. Do not filter it. Instead, what you do, you heat it back. You heat back the precipitate, the colloidal precipitate, within what we call as the mother liquor, the solution itself. Okay, the solution. So you reheat the solution and the precipitate. So when you heat it, what happens? All the precipitate will redissolve. Okay, so when everything is redissolved, so what you do, you off the heat. Okay, stop the heating, and then let it cool, and the process of precipitation to occur. So this process will produce large precipitate by the process of digestion. Okay, I repeat it back. So when you are producing colloidal precipitate, do not filter. Instead, you heat it. You heat back all the solution plus the precipitate. So the solution is called mother liquor, the precipitate is colloidal. So you heat it, and you will observe that the precipitate will redissolve. When everything is become clear, stop the heating, and then let it cool down. And in the process, you will observe that the precipitate that will form will be large, coarse, and large size. So this process is what we call as digestion. Let's discuss about impurities in the precipitate. We want to have a pure precipitate. As such, we want to know how impurities can creep into our precipitate, making it impure. So the first one is about the name co-precipitation. During the process of precipitation, somehow some compound are able to go into the precipitate, either being absorbed on the surface, or it goes into the structure of the crystal itself, either by inclusion or by occlusion. So this is while the precipitate is forming. The second one is based on post-precipitation. A foreign compound precipitates on top of the desired precipitate, meaning that after the precipitate had formed, okay, and we left it for a little while without filtering it, so some forms of impurities may form onto the precipitate. But we will not be discussing about post-precipitation, but our further discussion will be on co-precipitation. Okay, so goes back to the terminology. The precipitation of an unwanted species along with the analyte of interest. Okay, so along with the analyte of interest, we add Ag to chloride and the formation of Ag chloride, silver chloride. Okay, so a pure silver chloride will contain only silver chloride without anything on being absorbed on its surface, or part of the ions in the Ag plus or Cl minus being replaced by other ions, or within all the crystal structure. Okay, so this is what we meant. We are trying to prevent it, so that when we do the weighing is only due to AgCl and not to other atoms or other ion or others that may be trapped inside. Okay, the first one is based on what we call as surface adsorption. So surface adsorption is any impurities that may be trapped on the surface of the crystals. If you go last time during the double layer, we see that on top in the first layer of the crystal, there will be ions in excess of the same ions in the crystal. So we add Ag plus to Cl minus. As such, we expect there will be an excess of Ag plus, which will be in the first layer, absorbed onto the surface of the crystals. Okay, and in the second layer, there will be the spectator ions, nitrate, H plus, SI, depending on what salt you are using to be used for AgNO3. So then the salt is nitrate. Okay, AgNO3 is salt and the nitrate is the anion. Okay, now how can we overcome or remove the impurities? The first is always by washing. Okay, always by washing, because washing, we can wash this by spraying dilute electrolyte onto the surface. So we are trying to remove the adsorbed layer, meaning that those ions that are trapped on the first layer, and also the ions on the outer layer, the second layer. And the second layer is very easy. Even by simple washing of water, normally you can wash it. But to remove the first layer, the adsorbed layer, okay, because the Ag plus has some attraction to the chloride. Okay, so it absorbs onto the surface. It's quite difficult. So that's why, rather than use water, normally we would use dilute electrolyte, HCl, dilute HCl, dilute HNO3, instead of dilute HNO3, sorry, okay, instead of water. Okay, digestion, I will not suggest it, because digestion normally when we are involved, when the impurities are inside the crystals. Okay, digestion is being carried out when it's inside the crystal. On the top of the crystal, absorbed on the crystal, we normally use washing. Okay, let's have some examples over here. In determining sulfate in the sample, the sulfate was precipitated as barium sulfate, but the precipitate was contaminated. Okay, it's being drawn, the crystal, and then the first layer, and then the second layer. Okay, what is the precipitant used? Barium, right? Okay, barium is being used as the precipitant. What is the primary layer? The excess precipitant. So it must be Ba2+. What's the secondary layer? The spectator ion, chloride. Name the type of contamination. Co-precipitation by surface adsorption. So what is the surface adsorbed ion? Barium2+ and chloride. So how to remove it? So I said that when anything is adsorbed, the impurities are adsorbed onto the surface, the primary method is always by washing. Okay. Now the second one, what is meant by inclusion? It's a mixed crystal formation. So if you look over here in the diagram over here, so in the diagram, you see that these are the crystals. So these are all the crystal ions. And in all these crystal ions, one of the blue crystals are being replaced by the red crystal. So inclusion means that an ion, barium sulfate. So either the barium is being replaced by other cation, or the sulfate being replaced by another anion, for example. That's what I mean. Okay, so the crystal is now becomes impure because part of the crystal are being replaced. So this is what we call as inclusion. Interference are incorporated into the crystal itself. Okay, can occur if two ions combine with the same charge, So the same charge, Sr2 plus 113, and then Ba2 plus both have 2 plus, and then it may fit, the diameters may fit into it. So Sr2 plus replace Ba2 plus, okay, in one part of the crystal, so it becomes a mixed crystal. So this is what the examples of precipitate being unpure because of Sr2 plus replacing the Ba2 plus, and is called inclusion. Okay, and the third one, what is meant by occlusion? So inclusion is replacing, if I based on the diagram, Ba sulfate, it replaces the Ba2 plus or the sulfate 2 plus ions. But occlusion is when it says that you are not replacing any of the ions, but instead impurities are being trapped in between the crystals. In not replacing the ions of the crystal, instead some form of impurities are being trapped in between the crystals. Okay, in between. Probably my examples a little bit to the extreme, but I just create just to illustrate. Okay, you went to a roti canai stall, and they already make the roti canai. How do they make the roti canai? They tebai, right? So they make it, and then because of the long hours of work, okay, so wipe his head, and some of the sweat goes into his hand. Okay, and then he continues of his work, making the roti canai. Now, what happened to the sweat? The sweat is trapped inside the roti canai by occlusion. It does not replace the roti canai, but it is trapped inside the roti canai. I don't know whether this may explain it, but impurities are trapped inside the crystal without replacing any ions of the crystal. Okay, so this is impurities by occlusion. So there are the first one is by absorption on the surface. The second one is by inclusion, replacing one of the crystals, one of the ions of the crystal. And the third one is something is trapped in between the crystal. Okay, between the crystal. So it is by occlusion. So these are the three types of how impurities may affect the purity of the precipitate. Now, what happens? What happens when there is impurities? What happens when it does not become a pure crystal? Can you suggest? What happens to the weight of the precipitate? Is it increasing or is it decreasing? Of course, it will increase. Anything absorbed on it, it will increase. Anything entrapped in between it, it will increase. Okay, by inclusion, I'm just not sure whether it will increase or not. Okay, depending on the molecular weight of the ion that replace it. But by surface absorption and by occlusion, so the trapped material or the trapped impurities will certainly increase the weight. So what happens when we weigh the precipitate? Part of the weight includes the impurities, and we would not have the correct calculation of our analyte because the weight is more than what it should be. So that's the reason why we should try then to prevent impurities from creeping in, or if we found that there are some impurities, we shall have to do something. Okay, so if it is absorbed, we do it by washing, If it is include inside or by occlusion or by inclusion, then we would do the process of digestion. Okay, let's review the process. So in the first part, you prepare the solution. The second one, you add the precipitant and it forms the precipitate. So once you form the precipitate, what you do the filtering. Okay, so the filtration will help to separate the precipitate from all the other impurities that goes pass through in the filtrate and the mother liquor. Okay, so you are separating now the precipitate from the mother liquor and hopefully from other impurities. So there are many methods. Edgeless filter paper, seldom do I use it, but basically the principle is you do the filtration using the filter paper, and then when drying the process or heating process, the filter paper will be lost and it doesn't contribute any weight to the total the precipitate being burned or dried. Okay, the second one, the one that you use, okay, the use in the laboratory, okay, by using sintered glass filter crucible. Okay, this is what you are using. So you filter it and then you dry it in the oven or in the microwave and then the oven, or using sintered porcelain filter crucible. So for this, for higher temperature. So the choice of medium depends on the type of precipitate. Okay, but in our procedure we use sintered glass crucible. Okay, this is the setup that we have, but the setup is using Bushnell funnel. Okay, but we are using sintered glass. Okay, so this one is using Bushnell funnel. So the water aspirator, rubber tubing, and the filter plus. So again, I repeat back. When sometimes I observe in the lab that in the filter flask, okay, the filtrate, once you do the filtration, the filtrate will go to the filter flask, and I see red in color. So meaning that the nickel DMG form is very small. It must be colloidal. Actually, it's a mistake. Okay, a mistake in the Q and the S. There must be some mistake in it. Okay, otherwise you should have a very clear filtrate. Okay, so this is the apparatus here for the suction. Now, when you are finished with the filtration, so you should be doing what you call as the term washing the precipitate. Again, what's the function of the washing? To remove any impurities that are adsorbed or trapped on the surface of the precipitate. So I repeat again, the second layer is where your excess or your spectator ions are. So it's very easy to remove it by rinsing with small amounts of water. Okay, but those ions that are adsorbed on the surface in the first layer is quite difficult. It's quite difficult because it has an attraction. If Ag plus are being adsorbed, so Ag plus will have an attraction, electrostatic attraction with the chloride in the precipitate. So that's the reason why we would use volatile electrolyte, HNO3 for example. So rather than using water, we use HNO3, dilute HNO3 and do the washing by means of concentration. Okay, normally H plus cannot replace Ag plus, but when we use high concentration, although it's dilute by high concentration of HNO3, so that H plus from HNO3 will replace the Ag plus. Okay, and the Ag plus will be filtered out, goes down as the filtrate. And instead now on the surface of the precipitate, rather than Ag plus, it will be replaced by H plus. So will H plus be contributed to the overall weight of the precipitate? Yes and no. At this moment, yes. But after this washing step, we would go into the drying step. So H plus is very volatile. So when we heat it, so the H plus will be volatilized, leaving the precipitate to be pure. So that's why we are washing it with a dilute electrolyte. Okay, the other thing is that washing colloid with pure water will dilute it, and what we call as the process of peptidation. Peptidation, some of your precipitate will break off. Okay, will break off. Okay, so we want to prevent the process of peptidation, especially if your colloids, if your precipitate is a lot in the form of small precipitate, so it will further break off. So that is washing. Now, what's the function of washing? To remove those ions in the secondary layer and those in the primary layer, which is more persistent. Okay, now, how do we know that that washing is already being completed? A simple test. So we wash with we determine chloride ion by precipitate AgCl using AgNO3. Okay, then what do? We knew that we are now testing for the presence of Ag plus, whether it had already been totally removed. So we have a small amount of dilute NaCl or HCl, meaning that we want the chloride. Okay, so you do the washing. So while doing the washing and the filtrate coming out, so what do? Put into a test tube some chloride from NaCl or HCl. So you add some of the filtrate into that test tube containing chloride. So if there is still remaining Ag plus, okay, in the form being washed out, so it will then immediately form AgCl and it becomes cloudy. But if the washing step is completed, meaning that no more Ag plus, so the solution will remain clear. So that's how we test the completeness of the washing step, by using a chloride ion in the test tube and testing the filtrate whether it becomes cloudy. You need still to continue your washing, or if it is clear solution, meaning that all Ag plus had already been washed out, and you can stop the process of washing. So after you wash it, we make the assumption that everything now is pure AgCl and only some water. So this is the drying step. For AgCl, there is no ignition step, only for hydroxide. Okay, so we go to the drying step. So in the drying step, we are doing it by heating it at 110 degrees centigrade, okay, for 1 or 2 hours. Normally we do it by step, 1 hour, and then you will weigh it, and then continue weighing until the point where you arrive where we call it a constant weight. Okay, so the heating, after heating, you must cool it first before weighing. So cooling is carried out in a desiccator, and then you will weigh it, and then you will heat it again, and then you will cool it in the desiccator and weigh it again up to a point where the final to weight is almost the same, indicating that there is no more water. How many times do you repeat the process? Not sure, but you have to do it by trial and error. Now, why do we cool the precipitate in the desiccator? Why can't we immediately after heating we weigh the precipitate? Now, when it's heating, when we heat it, we are trying to remove the water. And when we are have the water, you see, our material will be we have a very high humidity. In the laboratory, very high humidity. So what happens? Water from the atmosphere will creep back into your precipitate. So you will observe that your precipitate will increase in weight, and the increase in weight will not stop. Okay, if you try after heating it and then you try immediately weigh, or if you cool it in the room temperature without a desiccator, you will see that you water from the atmosphere will being absorbed back into the precipitate. So once after heating, immediately put it into a desiccator where it will be cool without any addition of water from the atmosphere. So that's the reason why we heat it and then cool it in a desiccator to prevent water from the atmosphere from re-entering the precipitate. So this is examples of desiccators. So you will add below the part below, okay, those at the bottom, you will add some desiccant, copper sulfate. Okay, some examples of desiccant used for drying. Finally, you will go over to the calculation of the result. Okay, so again, the purpose of gravimetry is to determine the concentration of the analyte. In our case, most of the discussion, the analyte is in form of chloride, and we add the precipitant, it forms precipitate. And then when we weigh the precipitate, it should reflect the concentration of our analyte in the original solution. So this is how we make the calculation. Percent of A, okay, percent of A, whatever the analyte we wish, weight of the precipitate. So what is the weight of the precipitate? Weight of the precipitate when we finish our drying process. So we weigh it, that is the weight of the precipitate. What is the weight of the sample? Okay, when you use initially your solutions, that is in the form of weight, so that is the weight of your sample. If it is a solid sample, it's clear. Okay, the weight of the solid sample times gravimetric factor. So what is a gravimetric factor? GF equal to A over B times formula weight of the analyte, formula weight of the precipitate. Okay, let me explain. Okay, what is your analyte? So my analyte is chloride. So my analyte is chloride over here. So what is your formula weight of your precipitate? What is the formula weight of your precipitate? So your precipitate is AgCl. So can you have the formula weight of chloride? Yes, 35.5 AgCl. I'm not sure, Ag 35.5 plus Ag. So that is the formula weight of precipitate. Now what is AB? If you look over, so how do we do it? We cross it. I'll change the color. We cross it. Now look at, in AgCl there are how many chloride? 1. So we put it 1. So in chloride, how many chloride is 1? Okay, so 1. So in this, the value of A equal to 1, value of B equal to 1 times the formula weight of the analyte, chloride, and then divide by the formula weight of the precipitate. So that is how the calculation is. Okay, let's look at the next. Okay, these are for the examples of the gravimetric factor. Okay, so this one, if you look over, so calcium AO is the analyte, and this is the. So if you look at times A1, so this is on top, so that's 1, so times 1 over Ca is still 1. Okay, so this is we reverse it. We reverse the, if you observe just now, we reverse it. Okay, so that value of 1. So over this one is, there is 1 as and this is 1s. So what do you expect? The value is 1 over 1. Okay, so that is how we check the ion that want to give the value A or B. Over here is U 1 3. So UO is on the top, so it must be on the bottom. Okay, 1. And U3, when in the reaction, it is at the bottom. So when we reverse it, it becomes the top. So times 3, 1. Okay. So this one CR2 and this one is CR. So we expect this one is at the top. Okay, CR this at the top. So it must be in the bottom. It should be 2. And then this is 1. Because there is only 1 over here. This is 2. Okay. So this is how we determine the gravimetric factor. The formula weight of the analyte divided by the formula weight of the precipitate times A over B. Okay, finally we go over to the examples of how calculations are involved. A 0.4852 gram sample iron ore oxidized in acid to form Fe3+, was then precipitated as Fe2O3, actually hydroxide, with water. The precipitate was heated to form 0.418 gram Fe2O3. Calculate percent in the sample. Now, in the problem, the weight of the sample is 0.4852. Okay, and then it forms Fe3+, and then it formed here, and then finally it ignited to form Fe2O3. So what we are looking, finally, when you are reading the question, you always focus on what is the final precipitate being weighed as. Okay, now in this example, it's being weighed as Fe2O3. So do we have to be concerned with Fe3+ and then Fe2O3.X H2O? No, don't care about it. You must only focus to the final product in which is being weighed. That is the precipitate. Okay, and what is the question? Calculate percent Fe. So Fe is the analyte, and this one is the precipitate. Fe2O3 is the precipitate. Okay. So what is the, if we put into the gravimetric factor, formula weight is of analyte. So what analyte? Fe. What is the precipitate? Fe2O3. Now what is the gravimetric factor? So this one we go over here, right? So this one is 1, and the bottom, sorry, this one is 2, and this one is 1. So 2 over 1 times formula weight of Fe divided by formula weight of Fe2O3. So this is what the equation is, and it will give you 0.6997. And then you put it everything in the equation and will give you divide by the weight over here. So give you 34.86%. That is the percent Fe. Okay. Now, can you understand it? Okay, try to understand it again by reading it back. Okay, yourself. Now, if I were to ask you, instead of percent Fe, now the analyte is, I ask you Fe3O4. Aha. The product is Fe2O3. The analyte is Fe3O4. So can you calculate it and give me the answer? Okay, so instead of percent Fe, calculate percent Fe3O4. So what would then be percent of Fe3O4 being produced? So without changing the question, the process, I'm asking you, the first the analyte is Fe, the second one the analyte is Fe3O4. Okay, so by that, try it at home, try it and give me the answer. And if you try it, then that will signal the end of our gravimetry. Okay, thank you very much.